if these are leaves, then clearly they're going to pass up 2 endpoints and 2 endpoints. And so this guy will have 4 endpoints, so he can take 2 and pass 2 more up.
Can you say that again?
So the sets are collecting endpoints. We want each set to collect 2 endpoints because we know that the number of sets equals the number of edges, and
why do we know this?
This is due to duality. So these are all tight and linearly independent.
Oh, yeah. It's
and
the variable number is m. So.
Yeah, so the number of variables is m, so the number of tight constraints is also m. And so what we're going to do is we're going to use the endpoints to count the sets in some sense. We're going to take the endpoints from the edges and give them to the sets. And then what we're going to end up with is we're actually going to have leftover endpoints at the end. And when we have leftover endpoints at the end, that means the number of edges we had was strictly greater than the number of sets. But this can't possibly happen because we were at our basic feasible solution, which means our sets had to uniquely define the values on the edges. And in order for this to happen, since it's just linear constraints, then the number of sets has to equal the number of edges.
It could be greater or equal to, right?
Yes, the number of sets could be greater than or equal to the number of edges. But in fact, if we're taking a tight linearly independent set, and all the edges are entirely fractional,
Yeah.
then this will actually
There's
be
no
equality.
degeneracy basically then.
Right. Yeah.
Can you do the counting part again?
I haven't finished the counting part. So I'll finish the counting part and then I can do it again if you want. But I can't do it again before I finished. So we have every minimal set starts with at least 4 endpoints. And so since every edge has 2 endpoints, we want every set to end up with 2 endpoints. So we want every set to get 2 endpoints and then pass 2 endpoints up to its parent.
Do you mean you have like the cut, the cardinality of cut of their children will be greater than or equal to? Is that what you mean?
No. So so what I mean is every edge here starts by giving its endpoints to the smallest set that has that endpoint. So in this example here, this endpoint will go to this set, and this endpoint will go to this set.
You're saying at least 2 of those endpoints, or well, could there be a point that starts? Yeah, there could be a point that starts in none of the subsets, right? Yeah.
Yeah, there could be a point sitting out here, in which case it doesn't get assigned anywhere. That's still going to be okay because I'm still going to have extra endpoints at the end. And so what I want to show is at every step as I go up, everyone gets enough endpoints.
So can I ask why is it the case that I know why every minimal set has 4 endpoints, why is it true only for minimal sets?
So I'm just starting here. So this is like the base case. So every minimal set has at least 4 endpoints.
But is it not true for every set? In your linear family?
So you're only getting a endpoint when you're the smallest set containing it.
Oh.
Yeah. Yeah, so you do have 4 endpoints inside of you, but you're not necessarily the smallest set for those 4 endpoints. So every minimal set is good. It gets 2 and passes 2 up to its parent. We're good on the base case. Awesome. So now I'm going to consider the case where we have some set S with 2 children. or more than 2. By induction, both of these guys got enough endpoints, and they had 2 to pass up. So how many does S receive from its children? 4, yes. And so since S gets 4 from its children, it can keep 2 and then pass 2 up. So now there's only one case left. The case where you have a tight...
Can you say this again?
So the way we're going to give 2 endpoints to everyone is everyone's going to get the endpoints that they were minimal set for, and then they're going to get 2 and pass 2 up. We're good on the minimal sets, and we're good on the guys who have at least 2 children, because those guys get 4 from their children and can pass, so they keep 2 and pass 2 up. So the only case we're worried about is here we have a child and a parent S, and so S has just 1 child. So first of all, there has to be an endpoint which is in S, which is not in C. Because think of the different edges we can have here. The different edges we can have here look like these 3 possibilities. There's no reason why we should have any of these. I'm not even going to worry about if we have any of these. But what if we had none of these either? Then S is only getting 2 from its child. And 2 is less than 4. So we have a little bit of a problem here. And so, but if all the edges that cross S also cross C, so if all your edges look like this, then what do you know?
Dependence.
Yeah, you have a linear dependence because your constraint here is exactly the same as your constraint here. So that means you have to have someone that starts here and either goes into here or it goes out of here. But let's say you only have 1.
Then you have to place a third.
Sorry, I have XE is entirely fractional. So the thing is we still have to fix this up. The sum of all these is integer, and the sum of all these is integer. So there actually has to be someone else either coming into here or going out up there in order to make this okay. So in this case, S gets 2 endpoints on its own.
And we're using the fact that X bar B is less than 1/3 for everything.
Actually, we only needed that it was fractional for this case. The only part that we used X bar is less than 1/3 was for starting at the minimal
Why
size.
can't we do it with, like, let's say 3 edges?
So the thing is,
Because it can be 1/3, 1/3, 1/3.
this could be 1/3 here and 1/3. This could be less than 1/3 here and less than 1/3 here, and then everything's still okay. You might not get 3 edges here because this stuff is this is integer, and this is integer.
Sorry, I'm saying that you said that we need a 4th endpoint, a 2nd endpoint that's in S that's not in C, right?
Yes.
And I think that it doesn't that argument. So
why? Just
Why?
explain why.
yeah,
Why is it not 3?
why is it not 3?
Yeah. So let's pretend that S and C had the same value. So their f of S value was the same.
Okay.
Then I could put like a little epsilon here and a little epsilon here. And so the sum of these guys is the same as the sum of these guys. And they'll be the same integer. They're not linearly dependent because this guy has this edge, which this guy doesn't have. So you don't need a third guy.
Yeah, I don't know. I used to go back. Because if I'm the only one that's slowing people down, then I don't know.
Okay, so I mean, are you confused about why?
Why is it not requiring the 1/3 assumption here?
I mean, you're using the fact that one set is integral, the other set is integral, and everything is fractional. So if you have something else crossing, you need to have these two.
Oh, sure.
Yeah, so you need something, at least one thing crossing. And if you only have one thing crossing, then this is integer and this is integer, but the only difference is this part. So this also has to be integer. And so we need at least 2. Sorry, I thought you were saying that there had to be at least 3. But there could be only 2. So this gets at least 2, and it receives 2 from its child. So this set will keep 2 and pass 2 up. Then eventually we get to the top guy. Well, the top guy is a maximal set. He's going to be able to receive 2 and pass 2 up. So somehow I have 2 endpoints sitting around, and every set got 2 endpoints. So that means the number of edges I have has to be strictly greater than the number of sets, which contradicts the fact that we were working with an extreme point.
Can you repeat why that set can pass 2 points up?
That's
the
2
S.
points in.
So every set always passes 2 up
Yes, so C passes 2 up.
to S, and S has 2 endpoints of its own. So every endpoint is initially given to the smallest set which has it.
I see. Yeah.
All right. We're good? All right. So now, so you can think of this as we took each edge and we broke it up into half, and then eventually we ended up with each set getting 2 of these tokens and some left over. And that's how we showed it. So Jane's proof of the 1/2 is a very similar idea, except we're going to have to be a little more broader in our tokens. We can't just use endpoints anymore. And so the way this is going to work is we are going to, in fact, use fractional tokens. So what we're going to do is we're going to say, all right, assume that xe is less than 1/2 for all e. And of course, we're at an extreme point. We're going to work with laminar sets again. Now, instead of giving endpoints away, I'm going to be still looking at my endpoints, but I'm going to be a little more careful. So each edge starts with 1 token. And then I'm going to say E is UV. We're going to give XE to the smallest set containing U. We're going to give XE to the smallest set containing V. And then we're going to give the rest of it, so everything that's left over, to the smallest set containing U and V. Again, if there's an endpoint that's not in a set, then that just gets, that extra stuff is kind of just floating around and gets lost. But that's okay, because all I want to show is that given this, every set gets 1 token. And not only that, but I have leftover. So does everyone understand the scheme and the goal? All right. So let's look at some set S. We're going to have some children in here. And we have 4 types of edges. We have edges which go from children to children, edges which go from child to parent, edges which go from parent to outside, and edges which go from child to outside. So, how much stuff does S get? Well, S gets XE from these guys. So that's easy. We get X of this set. We get nothing from these guys. For E of CP, I'm the smallest guy containing this endpoint, and I'm also the smallest guy containing both endpoints. So I get XE and I get 1 minus 2XE. So I get some stuff minus X of E of CP. So this is just adding the sum of 1 minus X of E for E and ECP. Now for ECC, we only get this bottom stuff because both of the children both of these guys contained the endpoint. Maybe someone smaller contained it, but I definitely didn't get the money for it. So then I have plus ECC minus X of ECC. Okay, so, yes, thank you. So this looks kind of messy, just a little bit. So,
You explained the subscripts. What's PO, CC?
Parent.
sorry, these are
Child,
children, parent, outside.
Okay. So I was trying to guess that.
Sorry, I thought I said child to child, child to parent, parent to outside as I was drawing it. It's okay. So, this is kind of messy, but it turns out that all these X terms are actually really nice. So what is F of S? Well, S is a tight set. So it's just the stuff that goes outside. And now what if I look at all my children? So I'll call this child 1, child 2, up to child L. What is the second sum? What is the sum here? Well, I have all the stuff which goes between 2 of them. Plus all the stuff that goes across 1 of them. All right. So now I'm just going to take the difference of these two. So I get F of S minus sum I equals 1 to L, F of CI equals, well, these two terms cancel. X of EPO plus X of ECP plus 2X, minus X of ECC. So this looks really nice. Let's combine this all together. So we now have the number of tokens that x gets is f of s minus the sum I equals 1 to L of f of ci plus e of cc plus e of cp. So this tells us that the number of tokens s gets is integral. F of s is integral, f of ci is integral, and we have two sizes of sets here. So we know s gets an integral number of tokens. We also know, well, xe is positive because, well, xe is strictly greater than 0, and 1 minus 2xe is also positive because we assumed everything was less than half. So the number of tokens s gets is integral, and it's, in fact, this could potentially be negative because of this term, but we know it can't be because you either got 0 stuff or you got positive stuff. So we know this is non-negative and integral. So how do we show this is positive? So if any of these edges exist, you get some weight.
How did you say that it's not negative?
It's
The
non.
total number of tokens that they get, and that's the sum of a bunch of not strictly.
She has to show that the f of s
Yeah, why
is
is it-
bigger than.
No, I don't. No.
Just because of
The
So
left side.
this is this part here.
The number of tokens.
So-
it gets.
Either I started with 0. Well, I started with 0, and I either got nothing or I got some positive stuff. Yeah. So if I have ECC, then I got something. Because all of these are strictly positive, because we're entirely fractional. And we're strictly less than half. So if we have ECC, we're strictly positive, we're good, we got our 1 token. If we have ECP, we're strictly positive, we got our token. If we have anything here, then we're strictly positive and we're good. So the bad case is if the only edges I have look like this. And why is this problematic? It's linearly dependent. So the sum of these constraints is going to count each of these edges once. And this whole constraint is going to count all the edges once. And so these constraints are linearly dependent, but we assumed we were working with a linearly independent set. And since this can't happen, and this needs to get crossed, this needs to get satisfied, then it has to be the case that we got something. And since we got something, we know that this is positive. Since it's positive and integral, everybody got at least 1 token. So I wanted to show that the number of, I'm running out of space here.
Why is it enough to show there's at least 1 token? Shouldn't there be some set that gets strictly more than 1 for the contradiction to happen?
Yes, so that's what I'm getting.
Oh, sorry.
Yes, so that's the point that's missing. We need to show either there's some set that got too much or there's some leftover. So it's actually pretty easy to show there's some leftover. So let's just focus on the maximal sets. Okay, so there's some maximal sets here, or even just like this maximal set here. This guy needs to get crossed. If he gets crossed like this guy has xe that goes nowhere. that's strictly positive, we have some leftover token. Or it goes between these guys, and since these are two maximal sets, there's nothing larger which contains both of these endpoints. And so then the 1 minus xe, 2xe here gets lost. And so since you have maximal sets and they need to get crossed, you're going to have some extra token floating around somewhere. And so what that tells you is the number of sets is strictly less than the number of edges, because every set got 1 token and we have some extra token. And so that's how we get our contradiction.
I'd like to point out that that's an ingenious argument. I mean, I've seen it like several times, and every time I see it, I just go, wow.
Yeah, it's really cool. And I also always forget this little bit. I'm like, where is the extra lining around? Everything seems to work out so nicely. But all you do is you go and you look at the top, and that's where the little extra is hiding.
Not everything, so those, they can't just be from the top to the bottom, because that would be,
So
I mean, from like, some from the maximal, because the maximal has to have something leaving it.
these could be,
Because you have to have,
these could be in some small set here. But the thing is, I'm giving to the small set containing U and the small set containing V. There's no set containing this guy.
No, but I'm saying that the edges, there has to be some, that f of s is strictly greater than 0, right?
If
that's,
it was,
that's what I'm saying, right?
yeah, well, if it was 0, assume it was 0,
Yeah.
And it
there
was
would be
tight,
nothing leaving it.
then there would be nothing leaving it.
So
And
then,
so
why can't that happen?
because we assumed x of e is entirely fractional. And this is a tight set. Remember, we're working with a tight set.
So then all of those have to be 0.
So then all those have to be 0, yes.
Yeah.
And so then we shouldn't have been considering that guy in the first place.
Sorry, that was the part I was missing. Actually, I find this argument easier than the previous one, maybe even. Yeah, than the one with the 1/3.
Oh, okay. Yeah.
I mean, yeah, because here the
Because the tokens aren't
Well,
moving around.
it's so easy. It's like integral, right? So therefore, you have to like you start off with a bunch of integers.
Mhm.
You're going to end up with a bunch of integers, and then that's really nice over there. It's
Yeah.
that like two-sided argument to show that it's not positive and integral is really nice.
Yeah.
And then because of this, that it can't be non-zero. It has to be strictly greater than 0. So this at least 1 is leaving.
Mhm.
So that integer gets lost. I mean, that's you give out.
Well, you don't
it gets
even-
lost.
you
It
don't
can't be
even-
lost because you gave out the same. Yeah. So.
Yeah.
It's so cool.
Yeah, it's really nice. The thing is, I feel like this kind of magicked everything here. Like, oh look, like I just manipulated everything and it worked out really nicely. And so, the interesting thing about the second proof I'm going to show you is it's a lot closer to the endpoints proof, and so it's
Intuitive.
It's more intuitive. The tokens aren't being broken up into these small fractional pieces all over the place. And so I guess you can take your pick of which one you like better. Once I show you
I'm not
the
saying this
second
one's better. I'm saying the magic is pretty good.
Yes, it is.
Yeah.
All right.
Jenny, why do the edges of cross outside exist?
So one of these two has to exist.
Because f of s.
Because f of s is greater than 0. If it was equal to 0 and it was tight, then all the edges crossing it would be 0. But we assumed that xe is entirely fractional. As soon as an edge gets set to 0, you can take it out entirely. You never need it again.
Okay.
As soon as an edge gets set to 1, you can set it to 1 forever and forget about it. So anything that is set to integer, you can take out and then adjust your f and keep and resolve.
This is not, we have to resolve it. This is just for one simple subproblem.
Oh,
Sorry, could you repeat once more? Why do they exist? I mean, if they exist, they will have value. Yeah, I'm okay with that. But
So why does a maximal set exist?
an edge that's cross outside.
So a maximal set is tight and linearly independent. So let's say it was the sum of nothing is 0. Then that is linearly independent on itself. And so anything that is linearly independent and in our set means you have to be summing some things up to get something which is non-zero, because we know we're entirely fractional. So we know f of s has to be has to have something crossing it, and it has to have something value greater than 0.
Why is it that you can assume that nothing is 0?
If something is 0, then setting it to 0 forever will never hurt you.
Why?
But forever, you mean till the end of the solving of an entire process?
Right.
Okay, so
And-
why?
And so the thing is, at each step, you, once I set it to 0, I have a feasible solution even when it's set to 0. And so when I resolve, I can still get a new extreme point that's valid, and all those are 0.
So it's just saying that the subproblem is feasible.
The subproblem is still
And
feasible.
you don't care about optimality here, so you're just going to, you just care about feasible subproblems.
But like why? Like we want the optimal solution.
We just want something that's within a factor of 2.
Yeah, so we want within a factor of 2.
Extreme point of the subproblem, not the
There exists so it's feasible, so therefore there exists this extreme point of the subproblem, and if there exists an extreme point of the subproblem, it has that property.
So here's another way of seeing it. You're never comparing yourself to you're always comparing yourself to the cost of the solution when you first solve the OP. At every stage, you just argue that I'm getting something and I can compare it again to the original.
To the original, okay.
Yeah.
And now we are saying that if you put it to 0, it's
I'm not
feasible.
hurting.
Yeah.
Okay, so why it's feasible?
Because when I was doing the algorithm, when I set something to 0 and it was set to 0, if I take it out, take out something that is equal to 0, then it's still feasible.
That's
Yeah, sure.
And then when I round something up and I take it out, then what I had before was still feasible, and so I didn't need to have those xe's that were set to 0 to still be feasible here. So all I need is feasibility from step to step. All right.
I think about the leftover, it's also nice to think you can add one giant set that collects all of those like on the top level, and then that set will also have some some tokens collected, and that kind of leftover that you have.
Right. Yeah, but I don't think you can argue that the top guy, if you put somebody around like all the maximal sets, that might be everyone.
Yeah.
Yeah, but it might not get.
So you just repeat the same argument that you do in the induction, and
So in fact, it does get it. Yeah.
and it has an integral and whatever, so it has this one token and yeah.
It's not quite integral. F of S.
So the first claim that they make is that f of s is at least alpha of s minus beta of s. So this is their key claim that they use.
Sorry, but not entirely in a smaller set?
Yeah, so for example, this guy gets counted for beta s and gamma s.
Okay.
This guy gets counted for beta s but not gamma s. So this holds for all s when xe is entirely fractional, and we're also going to assume again that xe is less than a half for all e.
So you need both for S.
Yes. And so I'm going to show if this holds, then we have a contradiction. And then I'll go back and prove this claim. So let's go ahead and look at our maximal sets. We have our maximal sets. And let's look at this expression summed over all those sets. So I'll call this S1, S2 up to SL. We have the sum of f of Si is greater than or equal to the sum of alpha Si minus beta Si. Well, this is just summing over all the sets which are contained in here, including this one, all the sets in here, including this one, and so on. So this first sum here is just m. This is going to count every edge that's entirely within each of these. So these are the edges within the SI. So this expression here is saying the sum of the f of SI is at least the number of edges which cross the SI. All right, so let's consider an edge which crosses the SI. It can contribute at strictly less than half here and strictly less than half here. And so if we look at their contributions, then the
the way they're split up is the same. XE, XE, and 1 minus 2 XE.
No.
Whatever you do. doesn't
No. I'm just saying,
matter. It's some-
when I look at satisfying these constraints,
Oh, I see.
this is at most a half. And so it can help this guy. This contributes, when we look at this sum over the edges, it contributes at most half twice.
Sure.
In fact, it contributes strictly less than half. So we have all the constraints are satisfied, so the sum of the f of SI has to be strictly less than the number of edges which cross SI. So this first inequality holds because of this claim, which I haven't proven yet. And the second inequality holds by the fact that all the XE are less than half. And so we get our contradiction, and you look very unhappy.
No, I'm just thinking. I missed
Okay.
one step and now I have to catch up.
Okay, so we get our contradiction because our number of edges which cross SI is too small, because all the edges have to have small weight. They have to have weight less than half, and the number of edges which cross the SI has to be relatively small. And so you don't have enough weight there to satisfy all the SI.
What I'm confused about is how are you using that first inequality to get to the second? Isn't the second inequality just the fact of the f of SI?
This step here?
Yeah. Is that a step, or are those two separate?
So this is just M,
Yeah.
which is the number of edges.
Uh-huh.
And this is the number of edges which are contained entirely within the SI. So if I take all the edges minus the edges which are within the SI, I get all the edges which cross the SI.
I see.
This is the number, not the
Sorry,
SI.
I was thinking that the second one inequality follows from the constraints of the system.
No,
But it's actually it's the opposite. So it's, the constraints of the system would imply they're equal, right, or something like that.
So if you consider the last inequality, it actually says that the sum of f of si's is equal to the sum of all x's that cross si's. And now we are saying that the sum of all x's is actually less than the number of edges.
Yeah, gotcha.
And this is what we get.
Yeah.
So we know that this
Yeah, okay,
here,
that's good, yeah.
okay, all right.
Sorry.
All right, so this is the contradiction we're working for. So now we just have to prove this claim. So we're going to start with the base case, which is where our S is a minimal set. So if S is minimal, well, alpha S equals 1, because there's no sets inside it, it's minimal. And we also have beta S equals 0. if we had an edge that was entirely inside alpha f, inside of S, it doesn't cross anybody. So why is it getting value put on it? It's not in any tight constraint. So we have alpha S is 1, beta S is 0, and since S is tight, we also have f of S is greater than or equal to 1. So we're done in this case. So now the case where S is not minimal is slightly more complicated. And we have if we look at the number of edges, which are, we're going to have S, and then we're going to have all the children again. So beta of S equals all the stuff which is entirely inside S, not inside anyone else, plus all the stuff that its children has. And so if we use this inequality here, we get that this is greater than or equal to gamma of S plus sum of f of Ci, alpha Ci? Yeah, alpha Ci minus sum of f of Ci. And this is just applying the claim by induction. We're going up, and so we already did our base case, so it's okay for us to move up in this fashion. And the sum of this alpha Ci, well, I'm looking at all the sets which are entirely within all the children. So this part is just alpha S minus 1, because the only thing that doesn't get counted there is alpha S, and then we have the f of Ci. All right, so this is a little complicated and not quite what we want. We want to show that gamma of S is at least the sum of FCI plus 1 minus f of S. And if we can do this, then when we substitute it in here, we'll get our claim. So we're going to go back to our picture we had before, where we had our children to children edges, we had our children to parent edges, children to outside edges, and children to parent to outside edges. And so these are the 4 types of edges we have. So this is all the stuff which is entirely inside S, but not inside any of its children. So this is E of CC plus child to parent edges. And then we get f of Ci plus 1 minus f of S. All right, so the first thing we're going to consider is that we're going to do 2 cases here. We're going to do case 1, which is gamma of S is 0. So if gamma of S is 0, that means we'd have no ECC edges and no ECP edges. So that means the only type of edges we have are these 2 types. And we know, because from previously we knew if we only have the child to out edges, then we're bad, because then we have a linear dependence. So we have to have the parent, we have to have some edge which goes from the parent to outside. So that means the sum of FCI is strictly less than f of s. Because there has to be some stuff here which isn't in the other guys. And so this, we have the left-hand side is 0 in this case, and the right-hand side is at least 0 or smaller. Because again, all these are integer. So now we'll do case 2, which is a little more complicated. So in case 2, we're going to have to write out everything, unfortunately. So we have gamma s. We want to show that this is at least all the children stuff, so 2x of ECC plus x of ECP. This stuff will get added in the sum once and subtracted off here. We're going to get the stuff on the going out, and then we get our plus 1. This stuff is only negative, so we're going to say this sum is greater than or equal to, or less than or equal to, if we didn't have that sum. Yes. And this right here, this is the same argument we made before. How much stuff is here compared to ECC?
Wait, you're comparing these two?
I'm comparing 2 times x of ECC to...
That's less than
Less.
Yep. So this is strictly less than ECC. And likewise, this is strictly less than, is strictly less than ECP. Because this is even smaller. I don't even have a 2 out in front here.
Are you assuming that x of EPO is bigger than 1?
No.
So how do you get from the first one to the second one?
It's at least, it's only, this is only going to be, either I'm subtracting off
I think
0.
he's worried about the plus 1 that's not carried over.
Yeah.
Oh, sorry.
Okay.
I just forgot about it. So this is strictly less than this plus 1.
It is really important.
Yes, it is really important.
Oh, come on, it's just 1.
But this is an integer, and so since this guy is strictly less than this integer, then I can say, I can replace this here with this is, and I have, the reason I have strictly less is because one of these is non-zero. Because gamma s is not 0. And so we have is less than or equal to ECC plus ECP, which is just our gamma s.
So you can just drop it.
You can just drop it because this is an integer. Yep.
Not just, you have to add that equality sign.
Yeah. So we added the equality we made the strict inequality into.
It doesn't disappear.
Yeah.
It's used in a different way.
Yeah,
Yes.
you just fall out.
It goes away eventually. I just got rid of it a little too early. And so we know now this is true when S is, gamma S is 0, and I guess this was the gamma S was strictly greater than 0 case. And so this was all we needed to show f of s was at least alpha s minus beta s.
This is like exactly the same argument that was in the previous proof.
So the same argument occurs here.
No, like this inequality that we are proving is exactly
Yes,
the same.
yes, the
And like,
inequality is exactly
yeah,
the
and these
same.
alphas and betas is just collected tokens in the set S.
Right.
Yeah.
But the
And
stuff that's not here that is there is the integrality. It's like magic integralities.
No,
not the
exactly.
integralities.
No,
Not the
There- there's-
not the
there's-
integralities. The other one, the previous one where you like count both
No,
sides.
but if I told you this, it's believable that you can think about this. But if I just gave you the algebra and be like, hey, look, it works, it's a bit harder to see, oh, why does it work?
The whole point is
So-
the tokens are integral.
yeah, so you can think of this as like the first proof, where everyone takes a token and passes it up. So this is closer in flavor to the first proof where you had, you could, we were saying there was 2 endpoints at every step. There was either 2 endpoints or 4 endpoints. So we're saying you have 2 tokens or 1 token. And so this is more, you have some tokens and you pass it up, sort of flavor, as opposed to, I give you this magic way of distributing tokens and it works.
So let's thank Jenny. Yeah, I mean, but it is technically time, but I guess we can take more questions and then we can hang out. Yeah.
So in the paper, do they like have any idea how to use this for something, or is it just for fun?
I mean, it's like the whole paper itself is like 7 pages long, and two of that is actually talking about a different problem entirely.
Okay.
So it's a very short paper, and they're just like, oh, here's this cute new proof of Jan's algorithm.
So I'll send out email if we have it next week, but let's thank Jenny again for